I don't know if any of you are interested in veterinary school. Maybe most of those students would probably go to UC Davis, which specializes in that. We're going to talk today, just before our lecture starts, about a compound called xylazine that is important for veterinary medicine. I was looking through Google News feed, and I saw an article that talked about a molecule called xylazine. And the article's talking about xylazine, the newest killer street drug in Michigan. What you need to know. I think the title of the article presumes that everybody in Detroit is a drug user who needs to know about xylazine contaminating their drug supply. But the article says that adding xylazine to fentanyl, that's a far more potent analog of heroin, synthetic analog than heroin, increases the odds of an overdose. And apparently this is something that has been happening over maybe the past 10 years, 5 years in big cities like Philadelphia and Detroit. Opioids like heroin and fentanyl are relaxants and depressants. They relax you, so somebody figured, hey, why don't we add this compound that comes from veterinary medicine? They use fentanyl to calm anxiety in horses, in cattle. So if you're going to do a cesarean section on a cow and you need to calm that animal down, you put xylazine. Or if you're a farrier shoeing a horse, then you might use xylazine to calm the horse down so it doesn't kick you in the head or something. Let's go ahead and take a look at this compound xylazine. It is not approved for any human use, and the dosage form, which is usually an injectable liquid that they use for veterinary medicine, is not useful for mixing with powdered heroin. It's not clear quite where they're getting this powdered form of this compound xylazine. But what's interesting to me is that the regiochemistry, the structure of xylazine, looks very unusual to me. And that will be more apparent starting later in this lecture why this is an unusual substitution pattern. But if you want to synthesize xylazine, the obvious way is to take this industrial solvent, metaxylene, we'll talk about that, the word meta, and then nitrate it, right? You want to put a nitro group on there. We know how to put nitro groups on benzene rings. The problem is that if you nitrate this metaxylene, all of the nitro group goes right here on this position. You don't get any of the desired position if you're trying to synthesize xylazine. And we'll tell you about why that's true or give you a rule to think about. So some clever industrial chemists had to figure out some way to make this compound efficiently. And they developed a patented process that's extremely crazy temperatures, doesn't work on any other molecule. I'm not going to tell you the recipe because then you'll try to use it on my exams or something where it's not going to work. But if you want, you can look up that patent yourself. So there's a secret patented process that occurs at crazy temperatures that will replace an OH group. And I'm also not going to tell you how to put that on there until the end of the course, an OH group on a benzene ring. And that makes this amino substituted xylene molecule, and then they can complete the synthesis of this ring using chemistry that we might see coming up later in the course, or chemistry related to that. Okay, so that's how they make xylazine. On the street, it's referred to as trank. I guess that comes from horse tranquilizer or something. But an interesting substitution pattern, and that's really the subject of our in a big way, of what we'll be talking about today. Now let's go ahead and come back to where we left off on Monday. On Monday, I told you about the 5 recipes for electrophilic aromatic substitution, and we went into detail on the mechanisms for generation of those powerful electrophiles. Nitronium ions, acylium ions, carbocations, these chloroferrate, chloronium ferrate species. We talked about all kinds of arrow-pushing mechanisms. And today what I want to talk about is the issue of regiochemistry. So if you've already got a substituent on a benzene ring, like a methyl group, or 2 methyl groups, or however many groups, how do you decide where that second substituent is going to go? Because now, when you've got one group on the benzene ring, the positions are not all identical. And we have a way to describe this. Let's take a look at what happens if you chlorinate toluene, this industrial solvent. you'll end up getting 3 different products. But when I look at the yields, there's really only 2 products here. The 2% yield, we just discount that because that's not useful to anybody. And we have a way to describe the relationship between these 2 substituents on these products, on these substituted products. When the 2 substituents are directly next to each other, like this, we refer to that relationship as ortho. They have an ortho relationship. You could call that orthochlorotoluene. The IUPAC name would be 1,2. IUPAC, they like numbers. But this is an old Greek description that dates back to the 1860s. The organic chemists I feel like, were the first to get there with names ortho, meta, and para. So it bugs me when I see companies like Meta being created, because now I can't search for compounds like metachlorotoluene without coming up with a bunch of Facebook hits to Facebook. When the substituents are 1,3 relative to each other, that's referred to as meta. They have a meta relationship. And if they're on the opposite sides of the benzene ring, we refer to that relationship as para. So that's parachlorotoluene. That's an IUPAC nomenclature. And you can see that when you run this reaction, you basically get 2 products in equal amounts, and then some tiny, tiny amount of some other molecule that the meta one is so minor, we generally don't even talk about that. We just kind of assume the yield is 0 because it's not useful to do that kind of substitution. So let me go ahead and talk a little bit about the rates. Like, what's happening with those rates there on those reactions? So you can see here that if I have a methoxy group on a benzene ring down at the bottom here, if I do electrophilic aromatic substitution, if I do nitration, Friedel-Crafts alkylation, chlorination, bromination, the positions don't substitute at equal rates if there's an alkoxy group on the benzene ring. You can see here that there is a massive acceleration when the methoxy group is there for substitution at the ortho and the para position. And don't worry about 60,000 versus 20,000. Those are about 10,000. What you worry about is 60,000 versus 0.3. Essentially, you get no meta substitution there. If you have an alkoxy group on a benzene ring, your next substitution is going to give you a mixture of ortho-substituted and para-substituted products. And that's characteristic of what really makes this characteristic is that the fact that there's lone pairs on that alkoxy group. Now, if you have an alkyl group on a benzene ring, this is another major class of substituted benzene rings, like toluene or an ethyl group or a T-butyl group or a cyclohexyl group. Those also substitute faster at the ortho and para positions. I mean, essentially, the main products there are the ortho and para substituted products. Forget the meta substituted product. A 3% yield isn't useful to anybody. We can just assume that's 0 because you're not ever going to recover a 3% yield when it's mixed with those other things. Now, I'm using these numbers in comparison, the rates of these substitution reactions, in comparison to just a simple unsubstituted benzene ring, right? If the substituent is H, that's basically just unsubstituted benzene. Now, there are some substituents that slow down the electrophilic aromatic substitution reactions. So, for example, if you put bromine or chlorine or fluorine on a benzene ring, they slow down the addition of the second substituent. We talked about this with trinitrotoluene. If you have the first nitro group on a benzene ring, the second nitro group adds slower. So let's take a look at how halogens affect the rates. You can see that the rates are really slowed down. They're really slowed down at the ortho and para positions. Now, they are slowed down at meta, but not as much. So which product are you going to get? Ortho, para, or meta? You're going to get the meta product. They're all slowed down, but the meta substitution is slowed down the least. And so in this case, you would end up getting the meta substituted product if you add a second substituent to that ring. And with nitro group, you can see the effects are way stronger. Nitro groups really slow down ortho and meta. Now they really ortho and para. They really slow down meta, but not by as much. So if you can get a second substituent on there, it's not easy. Maybe you crank up the temperature, you up the concentration of the reaction. If you can get a second substituent to go, it's going to end up at the meta position because that's slowed down the least. Okay, so let me try to summarize these effects, and I'm going to give you, actually, let me talk about the origin of this effect. Why do you get these rate effects? So I want to start off by talking about what happens if you have groups that affect carbocations, because it's all about the Arenium cation intermediate in this reaction that explains everything. So the Arenium cation in this reaction, you're going to fall back on your knowledge of cation chemistry. Which things stabilize carbocations and which things destabilize carbocations. So you can see here that if you substitute at this ortho position, it's going to leave a carbocation right next to the first substituent that was on the ring. If that first substituent is a methoxy group or a methyl group or a chloro group or a nitro group, and you add the second substituent ortho, you'll end up with an unfilled an atom that doesn't have a filled octet, 6 electrons, a carbocation right next to Y. And so in this case, Y will strongly affect addition to the ortho position. It's either really going to slow it down or it is really going to speed it up. And so let's go ahead and take a look at what happens if you add to the meta position over here. There's 2 meta positions. They're essentially equivalent. I'm just going to do one of these positions. Or sorry, let's do the, sorry, I'm jumping ahead here. Let's do para because it groups together with ortho a little better, right? If I add to this para position at the bottom, it's also going to leave a carbocation, but until I draw the resonance structure of this, it won't be obvious why Y has such a powerful effect here. So when I draw this resonance structure, get used to drawing a resonance structures of Arenium ions. You can see, right, these are not different molecules, they're just different ways to depict the same molecule. So if I add to the para position, I also get a carbocation right next to this substituent Y. So Y has a strong effect, either slowing down or speeding up addition to the para position relative to that first substituent. Now when I come down to the meta position, if I try to substitute the meta position when there's a group on there, and I'm not quite clear why there's a plus charge here, that doesn't really, forget that plus charge next to the Y, that didn't belong. So if I try to substitute the meta position when there's a substituent on there, you notice the first resonance structure I draw doesn't have a carbocation next to Y. Maybe I can draw another resonance structure. Let's try to see if we can draw another resonance structure that puts that carbocation next to Y. So I'll use resonance there to draw this out. Here we go. Well, the carbocation in that resonance structure is still not directly next to Y. It's closer, but it's not on the carbon that's directly next to Y. Let me draw one more resonance structure. I'll use these pi electrons and I'll shift them over here. And what you'll see is that no matter how many different resonance structures I draw, when I put the substituent meta in the Arenium ion, I never end up with a structure where the carbocation is directly next to Y. And so Y, in this case, does not strongly affect addition to the meta position. It doesn't strongly slow it down. It doesn't strongly speed it up. It doesn't have a strong effect. It'll have a slight effect, but not a strong effect. So really, the first substituent on the benzene ring very strongly affects addition to ortho and meta, and doesn't have a big effect. It'll have a slight effect on, addition ortho and para. It'll have a slight effect on addition to meta, and it's not going to be a big effect. Okay, let's take a look at things that have lone pairs. Because if you want to have a strong cation stabilizing effect on carbocations, you want lone pairs on atoms next door. Let's take a look at amino groups. Those have the most nucleophilic lone pairs of neutral atoms. The lone pairs of an amine are more nucleophilic than oxygen, than fluorine. And so if you have an amino group with a lone pair right next to a carbocation, you'll get very strong stabilization of that carbocation. So whether the amino group ends up ortho or it ends up para to that substituent, that amino group will have a powerful stabilizing effect on that carbocation. So in general, any substituents that have lone pairs, whether those lone pairs are on an oxygen or on a nitrogen, or on chlorine, bromine, or fluorine, those lone pairs will stabilize the carbocation. Not equally, but they will stabilize the carbocation, right? Carbon wants to have a filled octet of 8 electrons. So those lone pairs help carbon to satisfy the octet rule. Another group of substituents that can stabilize carbocations are alkyl groups. Like if you had a methyl group or an ethyl group, or a propyl group, or a cyclohexyl group. Tertiary carbocations are more stable than secondary. So you'd like that R to be an alkyl group. If you had to put either an H or an alkyl there, you want it to be alkyl. So you want to end up with, if you have an alkyl group on your benzene ring, Arenium ions where you've added either ortho or para. Right? If you add ortho or para, then you'll end up with an Arenium ion that's like a tertiary carbocation. So again, it doesn't matter what the alkyl group is. Right? It can be any one of these types of alkyl groups. You're going to favor ortho and para substitution with those. Now, what happens if you have an atom that doesn't have lone pairs? An atom that is not a carbon atom, that is not an alkyl group? Well, it's not such a good situation there. Let's take a look at one of the substituents that really, really kills substitution ortho and para. Right? If you have a nitrogen atom, like an ammonium ion, we haven't talked about those. Whoa, I don't know what happened with that. If you have an ammonium ion, trialkyl ammonium, H3N+, it's still nitrogen, but notice there's no lone pairs on that nitrogen atom. Boy, that sucks if you try to make a carbocation right next door. Boy, that overall species has a +2 charge on that molecule. That's awful. No way you're going to make much of that. That's so difficult to substitute an Arenium ion in that way. And so what you'll find is if you have substituents on a benzene ring that don't have lone pairs, that have electronegative atoms with no lone pairs, well, and carbon I'll talk about in just a second, then you don't want to substitute ortho and para. Those substitute meta. Right? A nitrogen with a lone pair is completely different from a nitrogen that has no lone pair in terms of its effect. Now let's go ahead and talk about this carbonyl situation here, the carbonyl substituent. Right? If I draw a carbonyl substituent on an Arenium ion, here's my Arenium ion. Let's say I added my electrophile ortho. I'm not saying you could, but if you add that ortho to a ketone group, like an acetyl group, well, that's not good. And the way to see that that's not good is we draw another resonance structure. One of the things that we're going to see in this chapter, in this quarter, in the next chapter, the chapter after that, the chapter after that, is that you can think about carbonyl groups kind of like carbocations. If you give the electrons to oxygen, which is pretty reasonable because oxygen's electronegative, you end up with a resonance structure that looks like this, with two positive charges, two carbocations right next to each other. How is that going to satisfy the octet rule? Right? You got two carbocations right next to each other. That's no good. So that's a crummy situation. So that's why carbonyls are grouped together over here. Carbonyls are grouped together with other atoms that don't have lone pairs. So you have to draw a resonance structure to see that. And you may think, well, I don't really believe you, Dave. I don't believe that that's an important resonance structure. Well, get ready, because in the next chapter, over and over and over again, we are going to add nucleophiles to carbonyl carbons, because carbonyl carbons behave like carbocations. That's going to be the big theme of Chem 51C of this quarter. Okay, I have to talk about something really confusing, and that is that electronegative atoms like oxygen, methoxy groups, hydroxy groups, amino groups that have lone pairs have two opposing effects. And you're going to be confused by this. It's like, wait, you mean it can do one thing and then the opposite thing? Yes, that's right. Well, which one does it do more? I have to tell you that because you couldn't possibly know. Right? Whenever you have two opposing effects, I have to tell you which one is the more important one. So let's talk about these two opposing effects of heteroatoms that have lone pairs. So number one, heteroatoms that have lone pairs can destabilize carbocations. This is an electronegativity effect. If I look at the oxygen atom up here, oxygen has more protons in the nucleus than carbon. It's electronegative. And so if you put a carbenium ion, a carbocation, right next door over here on the bottom, that oxygen atom is going to destabilize this. This is called an inductive effect. Some books call it a polar effect. But this is the situation when you have electronegative atoms. They have more protons in the nucleus. Protons have positive charge. You don't want a lot of positive charge right next to each other. Coulomb's law, there's all different kinds of ways that you could rationalize why this is a sucky situation. So you don't want to end up with Arenium ions that have electronegative atoms right next door to carbocations. But let's talk about another effect of these of atoms like oxygen and nitrogen, and it is the exact opposite effect. Anything with a lone pair, even if it's electronegative, if it has a lone pair, can stabilize carbocations through resonance. So not only does an alkoxy group destabilize a carbocation, at the same time, those lone pairs are donating into this carbocation through resonance. This is a resonance effect. It's not an electronegativity, inductive, or polar effect. It's a resonance effect. So if you have an Arenium ion that has an atom with lone pairs on there, I'm not quite sure why all my atoms light up for some reason. I'm hitting something on my iPad here. If you have a heteroatom with a lone pair on it, on an Arenium ion, that can stabilize that carbocation. So there's two opposing effects here. Which effect is more important? Is it the destabilization of an electronegative atom, or is it the stabilization of resonance? This is an easy question to answer. Resonance is the more important effect. Oxygen and nitrogen, if they have a lone pair, the resonance stabilization is more important than inductive effects. And this is generally true throughout organic chemistry. For some reason, the book tends to just really love talking about inductive effects, but those are weak. Those are weak. Resonance donation to satisfy the octet rule, that's strong. It's the octet rule that's driving organic chemistry, for the most part, to a first order approximation. So resonance, right? This is the one right here. So oxygen, nitrogen, if they have lone pairs, they stabilize. They make things faster. They really drive ortho-para substitution because they lead to Arenium ions. If you substitute ortho pair, you get Arenium ions with highly stabilized carbocations. Okay, a minute ago, I was kind of jumping ahead. I was going to give you the big Uber table because I just told you a bunch of stuff to help you rationalize thinking questions and go deep. But let's just step back here and say, look, you just told me a lot of confusing stuff and I need you to simplify it. And it's all right here on this table. You need to memorize this table. This table summarizes right here everything you need to know about the speed and the regiochemistry for adding a second substituent on a benzene ring. If you have one substituent already there on the benzene ring and you add a second one through electrophilic aromatic substitution, you need rules, because I promise you I will ask you this. You need rules that allow you to predict where is the second substituent going to go. And this is the way you figure this out. Speed and regiochemistry. Let's talk about speed first. So if you have an atom on a benzene ring, I've got them listed here in rank order, you need to memorize this rank order. I've broken down this list in a way where you can see everything compared to a simple benzene ring where the substituent is H. Right? If the substituent is H, that's benzene. And I've arranged this so that everything above benzene reacts faster than benzene in electrophilic substitution, aromatic substitution. And the higher in the list, the faster it goes. So at the top of this list, substituted benzenes that react the fastest have amino groups on there. If you have an amino group with a lone pair, with a nucleophilic nitrogen lone pair, those undergo electrophilic aromatic substitution way faster than any other type of substituted benzene ring. Oxygen, not quite as fast, but still pretty fast. Second fastest. It can be an alkoxy group, it can be an OH group, it can be an acyloxy group like an ester, as long as that oxygen is on the ring. Now, esters and amides are not quite as good as just plain O-alkyl or N-alkyl, but they're still pretty good. So if you have an acetyl group on the amino group, I think if you're taking 51LC laboratory, you'll probably do some electrophilic aromatic substitution with an amide nitrogen directly attached to your benzene ring, because they want you to get out of their lab fast. They don't want you waiting 6 hours for your reaction to be finished. So they give you a substrate that reacts quickly. If you put a phenyl group, anything really with a double bond, but I don't want to put double bond because the problem is if you just put a simple double bond on a benzene ring, the double bond will react faster than the benzene ring itself because you don't lose aromaticity when you react to an alkene. But phenyl groups would be another example of a pi system on a benzene ring. Pi systems like CC double bonds, benzene rings, phenyl will accelerate the rate of electrophilic aromatic substitution on the adjoining ring. Okay, alkyl groups accelerate electrophilic aromatic substitution. Right? They lead to stabilized Arenium atom carbocations. So those are all the things that make it faster, and you have to memorize the order of this. I promise you, you have to know this. It doesn't matter whose organic chemistry class you're taking. If you take a standardized exam, they're going to ask you these questions, and they will assume that you memorize this list forever for the rest of your life until you finish taking tests that involve organic chemistry questions. Now let's take a look at the things that slow down electrophilic aromatic substitution. And this is ironic here. It's like, look, here's some atoms that have lone pairs on them. And it's kind of tough because they're electronegative. They're electronegative, but they're donated. They're electronegative, but they're also resonance donors. It turns out that the electronegativity effect matters most here, and you get slower rates of electrophilic aromatic substitution with halogens. So hold on, I'll explain how that makes sense with what I've told you previously, but it's slower. Chlorine on a benzene ring means the second substituent adds slower than regular benzene. If you have any type of a carbonyl group on your benzene ring, it can be a carbonyl with an alkoxy, like an ester. It can be an amide carbonyl. It can be a carboxylic acid carbonyl. If you have an aldehyde carbonyl, if you have a carbonyl group on the benzene ring, the second substituent will add slower. If you have sulfonic acids on benzene rings, the second substituent will add slower. If you have tetraalkylammonium type groups, trialkylammonium groups on benzene rings, no lone pairs on the nitrogen, that's way slower. And a nitro group, man, that just kills it. Just kills it. Really slows it down. You need to memorize the order of these. And I'm going to ask you questions where you have to know the rank order of these. Now let's talk about regiochemistry. We already talked about the speed of the reaction, but a separate issue. Yeah. Yeah, sorry, it depends on the R group as to which of those, and I couldn't figure out how to do it. It won't matter. I will never ask you a question whether you need to sort out nitro versus trialkylammonium. But it's great that you recognize that the nitro group and the NR, I don't know what NR3 group they chose in the book, have a different order. Memorize this rank order, right, instead of whatever's in the book. Okay, let's talk about the regiochemistry. You know, it's almost a perfect match between speeding up and slowing down versus ortho, para, and meta. But there is a maddening difference between the divisions of these two. Everything that is halogen or above in this list, everything, directs the second substituent to add ortho or para. Now, unfortunately, these stupid halogens, they slow things down, but they're also ortho-para directors. The lone pairs on halogens stabilize the Arenium carbocation. And so halogens direct the second substituent to go ortho or para. Anything down below halogens, like carbonyl groups, like sulfonic acids, alkylammonium, nitro, those end up directing the second substituent to go meta. They end up going meta on there. So those halogens are kind of, it's an annoying difference here. Let me see if I can use a red pen here to draw the two dividing lines. So for regiochemistry, the dividing line is at halogens, below the halogens. And for rates, the speed of electrophilic aromatic substitution, faster versus slower, the dividing line is just a simple benzene ring. And you've got to memorize both of these effects. You have to know which of these substituents direct ortho and para, and which of the substituents direct meta. And you need to know which substituents speed up and slow down, and by how much. That's the rank order. All right, let's go ahead and go a little bit further, because you're going to hear the word director, meta-director, ortho-para-director. Those are two common terms you see throughout the book, and they are incredibly confusing. That makes the term incredibly confusing. So nitro is one of the most powerful groups. Nitro groups are called meta-directors. They're at the bottom of that list. Nitro groups are meta-directors. So nitro groups, let me explain what does that mean when I say meta-directors, right? If I say that something is a meta-director, what do I mean by that? When the book says that, what does it mean? Here's the mistake that you will have a tendency to make. I hope you won't make this mistake, but it's all too easy because of the way the phrase is constructed, meta-director. So if you're going to nitrate a benzene ring that has a chlorine group on there, right, the tendency will be to think, oh, nitro groups are meta-directors, so they end up meta. That's not what meta-director means. It looks like it means that nitro groups always end up meta. That's not what it means. In fact, that's not the product you would get out of this reaction. You don't get this product out of that reaction. How do you figure out what product you're going to get? Well, I told you how to figure out the product you're going to get, right? If you nitrate chlorobenzene, what you have to look at is the first substituent that's on the benzene ring. That's the group that's going to determine where the second substituent ends up. And chlorine atoms and bromine atoms are ortho-para-directors, right? This is an ortho-para-director. You don't look at the second group you're adding, you look at the first group that was. So if chloro is an ortho-para-director, that means the second substituent is going to add either ortho, you'll get a mixture in this case, essentially an equal mixture, and para. And if I ask you the product, you'd have to write both of these products. Like if there's a box, draw the products of electrophilic aromatic substitution. Boy, that's a real pain, isn't it? What if you really wanted that meta-substituted product? Well, you're going to have to make that a different way. That's not to say that you can't figure that out. Right? If you're clever, what you'll figure out is maybe what I ought to do is I ought to nitrate the benzene ring first. Right? Just take benzene and nitrate it, nitric acid, sulfuric acid, and then in the second step, you do the chlorination. Nitro group is a meta-director. That means the second substituent, if you can get it to add, is going to add meta. Whoops, I don't want to put that there. So what's our conditions for nitration? I hope you've memorized these recipes, nitric acid and sulfuric acid. So there is a way to make that, but you just have to keep straight, what does it mean for something to be a directing group? It means if it's the first substituent, where does the second substituent go? All right, man, I've got some exceptions. You know, I told you when I introduced these 5 recipes to you that Friedel-Crafts would have all these exceptions. It's just a pain. Friedel-Crafts, I love making carbon-carbon bonds. You'd think that Friedel-Crafts would be my best friend in organic chemistry in this chapter, but it's just got so many exceptions. Let's start talking. It's like one exception is you have to add excess benzene when you do Friedel-Crafts, excess starting material. Well, that means you're throwing away most of your starting material, so that sucks. Here's another problem with Friedel-Crafts, is that our special order that I told you you have to memorize, you absolutely have to memorize it. For Friedel-Crafts, you also have to memorize these exceptions. Let me tell you about the exceptions for Friedel-Crafts reactions, for making CC bonds. So, special exception rule number 1 is you cannot do Friedel-Crafts reactions on anilines. Aniline has an NH2 or an NR2 group on your benzene ring, where it's dimethylamino, diethylamino, amino. Why is that? It's because the lone pairs on the nitrogen are so reactive that they react with the Lewis acid. Game over. You can't do Friedel-Crafts. The lone pairs are just so aggressive, they go after the Lewis acid before anything else happens. Special rule number 2 is you cannot do Friedel-Crafts if the ring has a meta-director. So any of these down here below are too deactivated. Turns out that carbocations are just not as reactive as nitronium or these chloronium ferrate species, or acylium ions and carbocations are not reactive enough once you deactivate that ring. So anything down below here is just not going to work, which you can't do. So there's only a limited set of compounds where you can do Friedel-Crafts reactions. Alkoxy substituted, amido nitrogen substituted, alkyl substituted, simple benzene rings. You can do it with a halogen on there because that's not a meta-director. But anything that's more deactivating than a halogen, that's out. So what would happen if I told you to synthesize this molecule right here that had meta-substitution between a nitro group and an acyl group? What this means is that you cannot take nitrobenzene and do a Friedel-Crafts reaction. If you take that standard recipe, you won't get any of this, right? There's no Friedel-Crafts if there's a nitro group on there. That's not to say you couldn't make that molecule. You just have to make it a different way. And there's some times where you can't make it any way. But I'm showing you a way. In this case, there is another way we could have made that. What you do in this case is you put the acetyl group, the carbonyl group on there first. Right? We know how to put carbonyl groups on benzene rings. I'm not going to write out the recipe. You take benzene, acetyl chloride, aluminum trichloride, and you put the acetyl group on first. And nitration always works with any substituent on there. We do the nitration reaction second. Acetyl groups are meta-directors, and acetyl groups don't slow down too much the nitration. Nitronium ions are so aggressive. They can easily do electrophilic aromatic substitution, even if there's an acyl group on there. Even if it's deactivated, you can still nitrate. That's not to say that it's just as fast as benzene, but you can still nitrate this ketone up above here called the acetophenone. So this is going to be a big theme of this chapter, is trying to see if you've practiced these reactions enough to be able to strategize how to synthesize molecules, where the regiochemistry is some non-obvious pattern. You're going to have to carefully choose the order in which you apply these reagents and then use these rules I gave you. You've got to memorize this kind of chart right here. Activated from most activating to least to most deactivating at the bottom. And then you have to know which of these are ortho-pair directors. And then you have to know these stupid exceptions for this Friedel-Crafts reactions, for the Friedel-Crafts acylations and alkylation reactions. Okay, let me just come back to the top of this list. Boy, when you have lone pairs on your next to your benzene ring, alkoxy groups and amino groups, those are so activated. Man, those react fast. Remember that methoxy example? And I said, oh yeah, 60,000 times faster. Sometimes things are so activated, it's just hard to control the reactivity. And I want to show you a special problem when you have alkoxy groups and amino groups on benzene rings for halogenation. And the problem that I'm going to outline here is if you have a phenol, that means hydroxybenzene, hydroxy groups on benzene rings. Not alkoxy groups, but phenol with an OH. You can't stop over halogenation. Right? If you try to take phenol and just add one chlorine substituent, that isn't going to work. So the problem is this reaction will keep going if you use your standard recipe. You're going to end up with chlorination. And so now you've got a mixture of chlorophenol and regular phenol floating around. And so the next thing that chlorinates is going to be the product. And you'll end up over-chlorinating. You cannot stop the product from continuing to chlorinate. And you might think, well, I'll just add one equivalent of the chlorine. You're just going to get a mixture of mono, bi, and trichloro, and that's not efficient. Every time I ask a question on my exams, I ask you to supply reagents to efficiently carry out transformations, not inefficiently and give mixtures of compounds. Nobody wants that in organic chemistry. So if you didn't add three equivalents, you'd get a horrible mixture that's not useful to anybody. So you basically, there's only one way to do this. If you want to use that Lewis acid, you just have to put in an excess. You don't get the compound, the monochloro compound, but at least you get one product. Now, there is a way to get monohalogenation. And the trick is to leave out the Lewis acid. So let me just write no Lewis acid. If you leave out the Lewis acid, phenols are so active with an OH on your benzene ring. It's so active you don't even need that Lewis acid, ferric trichloride or ferric tribromide in this case. So if you want to add one halogen on there, you'll get a mixture of ortho and para substituted. Then you leave out the Lewis acid. That's the trick. But if you put that Lewis acid in there, it's going to over-halogenate, and you can't control that. Now, with anilines, with amino, if you have an amino group on your benzene ring or a dialkylamino group on your benzene ring, dimethylamino, dipropylamino, just amino, there is nothing you can do. You are going to halogenate that whether you leave in the Lewis acid or leave out the Lewis acid. You're going to get over-halogenation here. Right? We don't have, so if R is just simple alkyl groups, not if R is a carbonyl, that's a different functional group. But if you have dimethylamino, diethylamino, right, so you might as well add three equivalents, so at least you get one and only one product, or excess Br2, but you can't stop over-halogenation. Well, and the book loves to trip you up with that. They make you go through all kinds of shenanigans later in the in the problems that's to try to get around that or make use of that, and it's I'm not sure why, so I'm just trying to prepare you for that. All right, so if you have one substituent on that benzene ring, you got to think carefully. You've got to memorize that chart. You have to. Every organic chemistry student, for any book, any course, has to memorize that chart and the rank order of those substituents. Which ones speed up and which ones slow down electrophilic aromatic substitution. And you have to memorize which of those substituents are ortho-para-directors and which of them are meta-directors. Now, why is the speed thing so important? Why is the rank order of the speed so important? I'm going to explain to you. Because if you want to predict what happens when you have two substituents, now you have to think about which of those two substituents are faster. When you have two substituents, you have to memorize that order from top to bottom to know which of those accelerates electrophilic aromatic substitution the most. And when I say accelerates, it could be deactivates less, but you need to know which of those two substituents is higher in that rank order, or there's no way to solve these kinds of problems that I'm showing you here. So here's the simple rule that allows you to sort out where the third substituent is going to go. And the simple rule is that the strongest activating group, there's two groups on there. The one that is the strongest activator, the highest in that rank order, is going to be the one that controls the regiochemistry. Let's take this first example here. So in this first example, I've got two groups on here, a hydroxy group. So that's a strong activator. That's right here in the list. That's a strong ortho-para director. And on the bottom, the methyl group is ortho-para, but it's not really so strong. It is ortho-para directing, but I'll say weak activator. It's still an activator, and it's also an ortho. So which group is going to control the regiochemistry? The hydroxy group. So we can, for now, let's just ignore the methyl. It's the hydroxy group that is going to control. And so if the hydroxy group is controlling regiochemistry, that tells us that it's going to cause the next substituent. I guess I don't want to use these red arrows. That looks like I'm doing arrow pushing. I'll use blue here. I'll just use some. So that hydroxy group is going to direct the next substituent to go ortho or para. And the para position is blocked. So it can't possibly add the next substituent para. So the product you get in this case, I'll draw it over here on the right side, is going to be bromine substitute. I left out the Lewis acid here, so you get monobromination. So this is how you use this rule. The strongest activating group controls the regiochemistry. You have to memorize the order of these substituents. Here's an example down below where I've got two deactivators. And this idea of strongest activator is kind of like saying the one that deactivates the least. So here I've got a deactivating group. Actually, it's not two deactivating, it's one deactivating group. So let's take a look at their effect. This one with the carbonyl group here is a strong deactivator. So I'll just write deactivator. Is it strong? Maybe I should say medium deactivator. But the one down below is an activator. So if I look at that list on the side, methyl groups are higher, alkyl groups are higher. It's the alkyl group, the methyl group, that will control the regiochemistry. And it controls ortho-para. And so this is the one. Up above, it was the hydroxy group. Down below, it's the methyl group. And that methyl group is going to direct ortho and para substitution, right? And the para position, once again, in this example, is blocked. And so the product is going to be controlled by the methyl group. And so the next substituent, which is a sulfonic acid functional group, is going to go ortho to the methyl. Okay, so I've shown you how, if you have one substituent on your benzene ring, to predict where the second substituent is going to add. I've shown you how, if you have two substituents on a benzene ring, to predict where the third substituent will add. And this opens you up to solve a large number of problems in organic chemistry. When you look at the approved drugs in the United States, like I don't know, it's like a 1.2 trillion, I don't know the number, $1.2 trillion market. Most of them are aromatic compounds. And somebody had to go in and figure out how to synthesize those using rules like this. You have to go out and know how to use these rules and solve problems. I'm going to give you problems. I promise you there will be problems on my exam. Every section of 51C, they ask you questions where you have to know and apply these rules for electrophilic aromatic substitution. And let me give you one last rule that will help you make sense of that thing that I showed you today for that drug, that horse tranquilizer drug. And the simple rule that we have is if we have two substituents, here's a case where I have two activating groups, identical, methyl. Now methyl, so I can pick either one, they're identical. Right? If it was methyl and ethyl, they're essentially identical. And so where is the third substituent going to add? Right? In this case, if I pick one of these methyl groups, I would say, well, that top methyl group will direct ortho and para. But now those positions are not all identical. Right? The position in between the two methyls is different from these two equivalent positions out over here. These two positions with the bigger dots are equivalent by symmetry. But there's a simple rule to help you figure out the product. That when you've got those two that meta substitution pattern, it's too hindered in between there to add. You don't get electrophilic aromatic substitution in between two groups. It's too hindered. So if we do a Friedel-Crafts acylation reaction, the product is very easy to predict. In this case, it's controlled by either one of the methyl groups. There's a symmetry here. And we don't get addition here to that middle position. The next substituent adds to it's ortho to one and para to the other methyl. It adds to ortho to one of the methyls and para to the other. So there's only one product in this reaction. So you don't get substitution between. Even if you want it, you can't get it to go in between there efficiently. So you now know how to do problems where if there's one group on a benzene ring, where does the second group go? If there's two substituents on a benzene ring, where does the third group go? And the book and my tests and problem sets are all about, here's some substituted benzene with 3 substituents. How do you make that from benzene? So you need to go practice that. You may think, oh, that's easy. No. You won't get it until you've practiced it a bunch, and then it'll be easy. Okay, so go work a bunch of problems to figure out how to use these tools. They're very powerful, and they'll teach you how to synthesize substituted aromatic compounds.